Hi, welcome to Recitation 9. What we are talking about today is basically the extreme value theorem, which talks about maximum and minimum values and points of functions. And here's the most important equation, derivative equals 0. So just as quick reminders, this is mainly what we covered during a lecture on this topic. There was a lot of terminology that we need to learn. I'm briefly reminding you about that in here. First of all, there are the words absolute and global, which mean the same thing. They refer to the entire domain of the function or entire interval that we are considering. And they stand in opposition to local, which refers only to points around the point being considered and does not apply to the endpoints of the domain. Like if a domain is an interval containing the two endpoints, a point can only be a local minimum or local maximum if it is inside in the open interval between 1 and 3. So it cannot be the points 1 and 3 in this case. All right, when we say point, we mean x coordinate. And when we say value, we mean y coordinate. The words extreme or extremum, they refer to either minimum or maximum. So both, if something is a minimum or a maximum, it can also be called extremum. And finally, what is a critical point? A critical point is a place where the derivative is 0 or does not exist. And also this concept does not apply to endpoints, a similar remark. If you're looking for the critical points of a function defined on the interval between 1 and 3 like this, it has to be a point inside, strictly between 1 and 3. And finally, what was the EVT, the extreme value theorem? It's just a theorem that we need to know about when a function has global minimum and global maximum values. And the way that you can guarantee that is if the function is continuous and defined on a closed interval. Whenever that happens, you know for sure that global min and global max must exist. Now, the other theorem that we mentioned, I think I never wrote this Fermat's theorem on local extrema. It tells us how do we look for local minimum and maximum points or values. Every one of those must be a critical point. So if you remember, this was the idea that if you're talking about points inside the interval of definition of a function, points where the graph attains locally at least a maximum or a minimum, so those are like the peaks and the valleys, so things like this, they must be critical points. So they must be locations where the derivative is 0, as you can see here, horizontal tangent lines, or might also be places where the derivative does not exist, like a cusp, so a function more like this. These points are local extreme points. I guess if you say points, it is the x coordinates, but they are local extreme points. And because in this case, the derivative does not exist, that's how the function managed to have peaks and valleys at those locations. Very last piece of reminder here, locating the extrema, the points. How do we find the global extreme points of a function? Well, based on everything that we just discussed, you need to find the critical points and you need to consider also the endpoints. The global extrema might happen at the endpoints. So basically you want to record the value of the function on every one of these candidates. If you're looking then for global min and maximum, just compare all these values and see which one's the largest and smallest. Now that's how these problems actually show up. And this is the plan for today. We're going to be solving many problems involving this procedure, finding maximal and minimal, or maybe just finding critical points, but of actual functions, not just graphical examples. So here's the first example. Find the global minimum and maximum points and values, so both x and y coordinates, of this particular function in the particular domain between -1 and 2. So first of all, analyze the endpoints. Analyze what the function is doing at the numbers -1 and 2. Whatever those values are, they could be your min and max globally. You don't know yet, but you should keep track of them. So in this case, f of -1 is 3. It's like 2 minus -1. whereas the cube root of -1 squared is just 1. Meanwhile, f of 2 is 0 because 2 minus 2 is giving you a 0. So we're going to keep these guys for later. These are candidates for global either min or max. That's the crucial word here, candidates. You don't know yet because you have more points to analyze. The other points that you need to analyze, I should have said endpoints up here, not just endpoint. So the other points that you need now are the critical points. These are going to be the locations inside of the interval where the derivative either is 0 or does not exist. So first of all, you're going to need a derivative of this function. I'm not going to put too much focus on calculating derivatives, but I'm just indicating here, how do you differentiate this crazy expression here, cube root of x squared? Well, that's the same thing as x raised to 2/3. So that particular derivative would come from the power rule, but you also need a product rule here because you have a product of two terms. So what do you get from the derivative? It's going to be minus x to the 2/3 plus 2/3, 2 minus x, x to the minus 1/3. Just use your product rule and power rule here. This is what the derivative is. And you have to say x different from 0. Why do we have to say that? Well, basically because you have x raised to a negative power. This number right here means 1 over x to some power. So the formula for the derivative is not defined for x equals 0. So in other words, 0 is a point where the derivative does not exist. So it is a critical point. All right, so f prime of 0 does not exist. 0 is a critical point. So what does that mean for us? We have to keep track of the value of f of 0 as well. Remember, this is because it is a critical point. It is a candidate for being a global max point or a global min point. So let's compute f of 0. Go back to the function, which is right here. Well, this part here, 0 to the 2/3 is going to give you a 0. So this is a value that we record for later. Maybe I should be circling these guys. All right, what is the very last thing that we need to do to find critical points? It's the locations where f prime can be 0 instead of not just d and e. So now take this formula that you found for the derivative. I'm copying that down here. And set that equal to 0. Solve for x. Okay, well, I'm going to move the x to the 2/3 with a minus sign to the other side as a plus. And then I'm going to multiply by x to the 1/3. Then the x to the minus 1/3 goes away, becomes just 1. And x to the 2/3 becomes x to the 3/3, which is x. So this is now a linear equation. Very easy to solve. I have the solution here, 4 over 5. This is another critical point, 4 over 5. So whatever value the function has at that point might be your minimum or maximum. So the function was 2 minus x. I'm calculating the value of the function now. X raised to 2/3. So cube root of x squared. Now this is just a crazy fraction number, irrational. You don't, I'm just gonna write the approximation for that. That's approximately 1.03. In an exam, you're not likely to find crazy numbers like this. It's gonna be something that you can easily compute. So, all right, anyway, values that we found. This concludes the whole analysis of every single point that could be a min or max. So what were all the values that I circled? They were 3 at the number -1, 0 for both 2 and 0, and then this crazy number for 4 over 5. Those were the 3 values. The global minimum value then is 0, the smallest of all. That's the y value equals 0. You can say just 0, y equals 0, f of x equals 0, something like that. What are the minimum points? Points, well, the locations where this happened, it was both at x equals 2 and x equals 0. If you remember, there were two places where we found a value of 0. And what is the global max value? The largest of the three values that we found, it was 3. The location where that happened, the global max point, this time there's just 1. So I'm going to write y equals 3 up here, and the x corresponding to that was -1. All right, this is the answer to the question. I'm going to add just something really quick here that's not part of the solution, but just so we visualize what's happening. This function kind of looks like this. It was the function defined between -1 and 2. You can see that the two values at the endpoints clearly indicate that this is the global max and this is the global min. The global min also happens here at the point where you have the derivative is not defined at this point. F prime does not exist because you have a cusp. And we also found one critical point here. This is the 4/5. But that value, the value of the function was 1.03. It turned out to not be either min or max compared to the others. This is what's going on. So I'm going to move on to this other question. It's slightly different. We're not asking for the max or min values. We're just asking for critical points. Find the critical points of the function. And if they don't say anything, it really means over its domain. They did not specify a domain for the function, so we're looking for the critical points over where it is defined. So the domain here, the only possibly problematic thing about this function is the square root. You want to make sure x plus 3 is larger than or equal to 0. So that means x is larger than or equal to -3. So the domain goes from -3 onwards, and you might include -3 in the domain. I mean, you have to, because it's larger than or equal. All right, critical points, by definition, they are points x inside of the open domain. So look at this. I am excluding the number -3 because by definition, critical points must be inside. So you never consider the end points. But anyway, they are points in there such that f prime is equal to 0 or f prime does not exist. This is what critical points mean. So we're going to be looking for those points for this function. All right, the function is x squared times x plus 3 to the 1/2. To find this derivative, you need the product rule first of all. Which is what I'm doing here. And then when the derivative hits the second term, the square root, that's a chain rule. So I'm also going to write that 1/2 x plus 3 to the -1/2 times derivative of the inner function, which is x plus 3. Well, the derivative of that is just 1. So this is f prime. You can see that the locations where this derivative is well defined, well, you have square roots, so you need x plus 3 to be larger than or equal to 0, but you also have them raised to negative powers. So that number has to be strictly larger than 0. Because essentially this negative power here means 1 over that number. So you don't want that number, x plus 3, to be 0. So the locations where the derivative exists is x larger than -3, which is good. It is every point in the place where we're looking for them. So critical points, they're not going to happen because f prime does not exist. It always exists in this domain. But it might be points where the derivative is equal to 0. So now we set that equal to 0 and solve. Let's see, 1/2 x squared x plus 3 to the negative 1/2 equals 0. How do we solve this? Well, first of all, right off the bat, you have x in both terms, in the terms being added together. So that x could be 0 to give you a solution, or if it's not 0, you can divide by that x. So like this, divided by the x. So we already have one solution here, and now we have to keep working with the second option to simplify that. Many things you can do here, but basically, for example, if you multiply by x plus 3 to the 1/2, it becomes a linear equation. I have it in my notes, so let me just write down the solution. Assuming I've done everything right, the solution should be x equals minus 12 over 5. Which, by the way, you should check. It does belong in the, remember this symbol here means belongs. Belongs in the domain where we are looking for these critical points, as well as this one. Also belongs between minus 3 and infinity. Minus 12 over 5 is minus 2.4, larger than minus 3. And 0 is also larger than minus 3. So these are valid critical points. And those were the only two that we found. These are the critical points of the function. They never asked us to find maximum or minimum values of this function, no. We don't even know if they exist, by the way, because the interval where the function is defined is not a closed interval between two numbers. It goes off to infinity. So in fact, the max and min might not even exist. But if they exist, these are candidates for locations where they can happen. But anyway, forget about all that. This is not what the question asked. We're done here. Next question, determine the maximum and minimum values of this function for the values of x between minus 2 and 2. Now we want to find maximum values. How does the procedure go? Well, we know they exist because the function is continuous, first of all, on a closed interval between minus 2 and 2. First, check what's happening at the endpoints. Find the value of the function at those two numbers. So f of negative 2, this is going to be minus 2 over 49. And f of 2 is going to be 2 over 49. And keep track of these numbers. They are candidates. We don't know what if they're going to be max or min yet, but you have to have those numbers in your analysis. Everything else, every other possible candidate must be a critical point. So you need to find f prime, and then you need to either set it equal to 0 or see where it does not exist. F prime here requires the quotient rule. I'm going to be applying that in here. You have low d high. D high is just 1 minus high d low. How do you find d low? That's a chain rule because you have something squared where that something is also a function. So according to chain rule, really quickly here, the derivative of the outer function, which is the square function, would give you 2 times the inner function. And this gets multiplied by the derivative of the inner function, x squared plus 3. That is a 2x. The whole thing should be divided by low squared. All right, this is the derivative. You see that you're always going to be needing these derivative formulas. You should be very familiar with these at this point. So, okay, what do we do with this? Well, the derivative exists for OX, even real numbers x, not only the ones in the domain of the function. There are no problems with this derivative. There is a denominator, it's true, but that number is never 0. You have a strictly positive number with a square plus 3. This is never going to be 0. So there are no problems there are no points where the derivative does not exist. But we can try to set it equal to 0 to find the places where it is 0. What does that go? How does that go? Well, essentially, only the numerator has to be 0. If f prime has this fraction in it, there is a denominator, but when you set it equal to 0, if you cross multiply, the denominator has no effect. Only the numerator has to be 0. Now let's solve this. What I'm going to do is I'm going to move the negative to the other side. First of all, you have 2x times 2x, 4x squared. And you have this term x squared plus 3 on both sides. As I said, that term is never equal to 0. So it's okay to divide by it. Divided by x squared plus 3 on both sides, because that is never 0. Right? It's a square plus 3. So we can do that to simplify the equation, and now you see that the equation becomes x squared equals 1. You have 3x squared equals 3, so x squared equals 1. Then x equals plus or minus 1. We find 2 critical points, plus or minus 1. They are actually inside of the domain where we look for critical points, the interval with open ends, right? Minus 1 and 1 are between minus 2 and 2, as given by the problem. So we do need to find the values of the function, f of 1 and f of minus 1. Now you go back to the function, and you plug in 1 and minus 1. You're going to find 1 over 16 and minus 1 over 16. With this, you're done finding all your candidates. Values found. Remember, we found plus or minus 2 over 49 at the beginning, the values at the end points, and now plus or minus 16 for the critical points. Now you just have to look at them and decide which one is larger, which one is smaller. Well, I guess you can do this without a calculator, but you can also just compute these guys. Turns out that 1 over 16 is a little bit larger. Yeah, this one is approximately 0.0408. Anyway, 1 over 16 is larger. So that means that out of these 4 numbers here, the largest is 1 over 16. The smallest is minus 1 over 16. So global max, let me write it this way, value, global max value is 1 over 16. That happens at the point where x is equal to 1. Right here, f of 1 is 1 over 16. And the global minimum, just put minus signs in these guys. Value is minus 1 over 16, point minus 1. So basically this function, again, this is not part of the solution anymore, but so you can see, remember the function was defined between minus 2 and 2. It had a certain negative value at minus 2 and a certain positive value at 2, but it actually was doing this. The global max and min values happened at 1 and minus 1. Those values were 1 over 16 and minus 1 over 16. This is what the function looks like. Moving on. Now I'm going to give you a piecewise function. We're going to need to think about what we're doing. So suppose that you have a function f domain between 0 and 10, defined by two different pieces with the break happening at the number 8. So here are the pieces. First of all, item A is saying, check that f is continuous and explain why the minimum and maximum values must exist over this interval. So checking that this is a continuous function, the only possibly problematic place is the number 8 where the break happens because the expressions are continuous expressions. So what you have to analyze is f of 8 equal to the limit of f of x as you approach 8? Is that going to be true? If it is, then the function is continuous. And this is an easy calculation to do here. You're essentially plugging in 8 for both terms and seeing if it's equal. So f of 8, according to this less than or equal sign right here, f of 8 is calculated by the first expression. F of 8 should be then 8 squared minus 6 times 8 minus 1. That's 15. And the limit, well, because it's a piecewise function defined by different pieces, the limit from the left is the limit of this expression on the left side of 8, so x squared minus 6 minus 1, as x approaches 8. That is a 15. And the limit on the right is also going to be a 15. This time, you're calculating the limit of this exponential expression. As x approaches 8, the exponent is 0, e to the 0 is 1, times 15 is 15. So, all right, all these numbers are the same. That means the function is continuous on the number 8, and is also continuous everywhere else. So finally, explain why the minimum and maximum values of f must exist. How does that happen? Well, remember the EVT, extreme value theorem. If you have a continuous function over a closed interval like this, global min and max always exist. They never said global, by the way, but that's what they mean, right? The minimum and maximum values over the interval. That means the absolute largest and smallest. So EVT, extreme value theorem, because f is continuous, on a closed interval of the form AB, the global min and max exist. All right, so we know they exist. If nobody asks, then you don't have to do this. You don't have to check. Like we never did this for the previous problems. We just went and found them. But now item B is, what are those values? All right, so now B is similar to the other items, other problems from before, except that this is a piecewise function. So what do we do in B? If we're looking for global values, global min and max, first of all, let's find the values on the endpoints. So if you try to find f of 0, you're going to need to use the first formula. It's going to be a -1. And f of 10 is going to be with the second formula. I guess it's 8 minus 10. That's going to be the number 15 e to the -2, or 15 over e squared, if you will. We don't have to approximate this number with decimals. We're not going to need to know what this is. You're going to see why. Next, derivatives. Critical points. So I guess we should at least write down this. This was the analysis of the endpoints. And now we're going to do critical points. So f prime, what is f prime? When you have a function defined by two pieces like this, the derivative that you can take by the derivative rules, like differentiating each formula, that's not necessarily going to be valid at the breakpoint, at the number 8, right? Even though the first formula is true at 8, but when you take a derivative using derivative formulas, all you know is that it's going to be true in the open interval. But okay, what is the derivative going to be? The first one is easy, 2x minus 6. For the second one, you need a small application of the chain rule here. Essentially, there's going to be a -1 coming from the derivative of the inner function. But we can now find these derivatives, 2x minus 6 and minus 15 e to the 8 minus x. That minus outside is the chain rule minus. So as I was saying, all you know so far is that these are only valid on the open intervals where the original expressions were valid. You don't know about the extremes. In particular, you don't know about the number 8. So f prime of 8, though, does that exist? And the answer is we can try to find out. I'm going to write this in red, by the way, because we don't need to do this part in the problem. You're going to see why. By definition, what is f prime of 8? This is the definition of a derivative. You have to use this if you have a piecewise function like that. So you would need to analyze this limit from left and right, see if it exists, in order to understand if the function is differentiable at 8 or not. But let's not do that, because remember, we're only doing this to find if the function is differentiable or not at the number 8, to find if 8 is a critical point or not. Well, it is just a point. You might as well keep track of the value of f of 8. Remember, it might be a candidate. If 8 is a critical point, we don't know, but let's keep track of the value. And we already found this was 15. So just keeping track. Keeping track of value at possible critical points. So this is another value that we should remember for later. In general, you always want to do this with a piecewise function. The breakpoints, like the number 8 in here, they are possible places where the function can have a critical point. Maybe the two pieces are joining with a cusp, a sharp corner, or maybe they're joining in a way that the derivative is 0 there, so it might be a critical point. Other than this, then we just need to find the other places where the derivative could be 0. So we're going to be setting each one of these pieces equal to 0 to see other locations where f prime could be 0. Might be the first piece, 2x minus 6 equals 0, or the second piece, minus 15 e to the 8 minus x is 0. Okay, the first piece is very easy. This gives you the number 3, which is valid for the first piece, by the way. Remember this first piece of the derivative, that was the formula for the derivative between 0 and 8. You found the number 3. That is to be considered. That's one possible point in here between 0 and 8. So that is a location where the derivative is 0. Now the second piece is not going to give you anything. Basically, you can divide by this minus 15. You just have the exponential equals 0, and that just never happens. Exponentials are never 0. So you just have one critical point, one point where the derivative is 0. It is x equals 3. Let's record the value of the function. How do you find f of 3? Go back to the original function. Here is the function. F of 3 is found by plugging in 3 into the first expression. So 3 squared minus 6 times 3 minus 1. That's a minus 10. And now you're done with the analysis. So as I said, it doesn't matter if 8 is a critical point or not. We don't know that, but it was just one extra value to record. These were all the values that we found. Okay, what is the largest? 15 is the max. You can see that because, well, the only two positive numbers here are 15 and 15 e to the minus 2. But e to the minus 2 is a number that's between 0 and 1. So when you multiply 15 by that, you get something less than 15. So that's how I know the first one is the second one here is the max. And the min is minus 10. So global min value is -10. Point is where that happened. You go back into your calculations and you see where did you find the place where the value of the function was -10? It was right here at 3. That's the x coordinate. And global max happened at the point 8 with a value of 15. This is the final answer to the problem. I'm going to once again just point out what's going on with the graph. This is not part of what we have to do, but I mean, eventually we are going to want to do this with functions. We're going to want to draw graphs. This function was defined as 2 pieces with the break happening at the number 8. And as it turns out, I guess it's mostly negative here. Between 0 and 8, it was given by this quadratic function, so a parabola. And it was more like this, where 3 was a critical point because the derivative was 0 there. And then it reached the value of 15 up there. After 8, the function became this exponential where the x appeared in the exponent with a negative sign. There was also a 15 in front. This is a decreasing function because of the negative x. So this function actually does this. So as it turns out, if you try to compute the derivative at 8 using the piecewise definition, using the one-sided limits, you're going to see that it does not exist. There is a sharp corner there. So 8 actually is a critical point, but we don't have to know that. We just recorded the values. This one, this one, this one, this one, and we found the maximum and the minimum. This is what we did in this problem. Next one. Determine the maximum values of, this is going to be an easy one, sine x times cosine x between 0 and 2 pi. And points, there's really no secret to this problem here. What is f of the 2 locations where the interval starts and ends? F of 0 is going to be sine 0 cosine 0. F of 2 pi is sine 2 pi cosine of 2 pi. Doesn't matter. Sine of 0 and sine of 2 pi, they're both 0. So the function is 0 at both endpoints. Critical points. Find f prime, set it equal to 0. Okay, f prime is going to take a product rule here. I'm going to apply that. When the derivative hits the sine, that becomes cosine, times another cosine makes cosine square. And when the derivative hits cosine, that makes minus sine. So this is f prime. F prime exists for OX. This should be in your solution, by the way. It is part of the analysis, right? There are no locations where f prime D and E, but that has to be said. So we know that you are actually doing that. You're verifying this. So that's okay. This expression is well defined. But when is f prime equal to 0? So cosine x squared minus sine x squared equals 0. How would you solve this equation? Okay, here's how you think about this. When you set something equal to 0, basically you want to factor as much as possible the left-hand side so that it becomes a product of things equals 0. Because when a product is equal to 0, one of the things at least has to be 0. So if you factor this difference of squares in this form, cosine plus sine, cosine minus sine, then one of those being 0 is what you need to do to solve the equation. Two possible scenarios here. Cosine plus sine equals 0 or cosine minus sine equals 0. So if you move the sine to the other side, you're basically looking for the points where cosine is equal to sine or to negative sine between 0 and 2 pi. Just think about your unit circle. You should know the answer. When are cosine and sine equal to each other? So you are at these 45-degree angles. These are the 4 locations where both cosine and sine are equal or minus one another. So you can solve both of the equations together by saying those are the x values: pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. The only places where this can happen. So you need to find the value of the function at each one of those. As they're going to be your candidates for global min and max. In this case, both of these sine and cosine are root 2 over 2. When you multiply, these give you 1/2. The other ones, they're going to be minus 1/2 or plus 1/2. Like this. Basically because at least one of the numbers, either the sine or the cosine, is going to change sign. It's going to change from plus to minus, let's say. So anyway, these are the values that you can find for this function at the critical points. Compare these to the values at the endpoints, which were 0. What are the max and the min values? It has to be 1/2 and minus 1/2. Okay, so I think the question was only asking for the values. Yes, no points. So we don't have to say where they happen. It's just the values. But yes, definitely this needs to be part of the solution, even though these guys turned out to not be the extremes. Doesn't matter. You have to have analyzed them. But later, when we found the values at the critical points, we realized these were the maximum and minimum values. So that's the answer. What is actually going on with this function, by the way, you probably know that sine of 2x is equal to 2 sine x cosine x. The function that we have is the same without the factor of 2, so like this. So the function that we have is actually in secret the sine function, only divided by 2 and applied to the number 2x. So it does something like this. 2 full oscillations like that between 0 and 2 pi. As you can see, the values at the extremes are 0, and the values at 4 critical points inside are 1/2 and minus 1/2. We could have realized this. We could have analyzed the whole problem without doing this calculus procedure, but we did not have to. The point is doing the calculus procedure, actually. This is also a very quick one. It's going to be the last one for today, because it's a polynomial function. So in this problem, you have an astronaut firing herself out of a cannon on an alien planet. The gravity is not the acceleration of gravity on Earth. The height above the ground is given by this function, where t is seconds, h is meters. What are the maximum and minimum height above the ground during the time interval 0 to 3? This is the interval for the variable, the independent variable t. So it's more like a word problem, but they are secretly asking for max and min. And global, right? During this interval, what is the maximum and minimum height? Height is the value of the function. So that's how we know that we are looking for global maximum and minimum values. The procedure is the same. You find it on the extremes. H of 0 is 40. H of 3 is also going to be 40 if you plug in 3 into the formula. And so endpoints. Now you analyze critical points. H prime is minus 2t plus 3. Exists for all t. I'm going to write all t in the location where we are interested. If we're looking for critical points over this domain, then it has to be between 0 and 3 strictly. But actually, it's true that this exists for any real number t. It's just that we only care about these ones right now. So it does exist for all. There is no place where the derivative d and e. That's usually going to be the case, by the way. However, you will usually find at least one location where the derivative is 0. So in this case, minus 2t plus 3 equals 0 gives you t equals 3 halves. This is a critical point. So you want to know what the value of the function is there. You're going to plug in this value into the original function. That's what I'm doing right here. And you find like 40 plus 9 over 4. I'm not even converting to decimals. We can already see this is larger than the two other ones that we found for the endpoints. So the max height is this little bit more, with the minimum height being both the two locations where it happened at 0 and at 3, the value was 40. This is the answer to the problem. What is actually going on in the problem is, once again, just something like this. This h function describes an upside down parabola where the maximum actually happened at the critical point, 3 over 2. Whereas the two values, 0 and 3, were both at the same height of 40. But once again, we don't need to do this in the problem. This graph, I'm just pointing this out. The solution stopped right here. All right, we're out of time for today. I'm not going to do the other problem that I had. I think these are more than good enough